Uh-huh. So all the speakers, please come to the first row here. So good afternoon, everyone. So welcome to the session on machine learning for computer vision 2. So my name is Zhou from Postech.
And I'm Bharat from Cornell.
So in this session, we have 4 oral presentations, and each talk will be composed of 12 minutes, followed by 2-minute question answering. So please be punctual, all the presenters. And okay, the first talk of this session is learning to find good correspondences. The talk will be given by Eduard Trulls.
Hi, I'm Eduard Trulls, a postdoc at EPFL, and I'll be presenting our work on learning to find good correspondences in the context of sparse key point matching. So in this work, what we want to do is to reformulate the matching step in traditional stereo algorithms, but now with deep networks. So the problem looks something like this. Given 2 images, the first step is to extract features for both of them and build a set of putative matches. Then we would use a robust estimation algorithm such as RANSAC, typically in an iterative fashion, to find a subset of inliers which conform to a given geometric model. From this, we can use the information that we have obtained to register the images and retrieve the relative camera motion. This has not changed all that much over the past few decades until very recently. Over the past couple years, there has been a strong push towards solving this problem with dense neural networks. Note that these approaches are dense, so they take the entire images as input and try to recover the pose. They have proved quite successful, but focus mostly on sequences with a small displacement, so video. And the general case, which is wide baseline, is still far from solved. So what am I talking about? Imagine we are trying to register these 2 images. Note how, in addition to significant changes in perspective, illumination, weather, imaging due to using different cameras, occlusions, we also have to deal with the fact that we have different aspect ratios, and sometimes only a small part of the image is visible across both views. This is something that sparse methods are traditionally better at. Even so, failures are pretty common. So here, for instance, I showed the inliers estimated by RANSAC for these 2 images, in green if they are correct, and in red otherwise. And as you see, the method is failing. So we are presenting a novel approach to solve this problem, now with a deep network, by relying on geometry to train it. So we have a geometrically aware deep network, which takes as input only the correspondences, that is only pairs of key point coordinates, exactly the same input as we would have in traditional methods, and produces 1 weight for each correspondence, which indicates their probability of being an inlier. We show how to train this network by learning to perform outlier rejection so that the inliers are consistent with rigid motion as encoded by the essential matrix. Okay, so what we want to do is to train the network with the essential matrix as ground truth. We could do this in different ways. One closed-form technique to retrieve the essential matrix from a set of correspondences is the 8-point algorithm. So it goes like this. Given n correspondences, we build an n×9 matrix as the outer product of each correspondence in homogeneous coordinates. Then we multiply it with its transpose, compute an SVD, and we have the essential matrix. That, however, requires clean input data, as it is not robust to outliers. We do have outliers, so what do? We propose to incorporate the weights generated by our network into the 8-point algorithm by simply applying them into the construction of this matrix. And what this will do is it will attenuate the effect of the correspondences that have a high probability of indeed being an outlier. And in this manner, we can have a version of the 8-point algorithm that is robust to outliers and use it to learn the weights for our network. Note that all of these operations are fully differentiable, so we can train this whole thing end to end. However, so one could expect or hope to use this approach to learn outlier rejection implicitly as part of the post-regression problem, which is what we're trying to do. It's all a matter of just finding the right weights. But we have a large ratio of outliers, and this seems to be too challenging. So the training does not converge to a good solution. It needs more help. We propose to give it more help by framing outlier rejection as a classification problem. So we can do this by using the epipolar geometry. Specifically, what we do is we compute the symmetric epipolar distance for every correspondence and just threshold it to generate training labels. So this is an example. I'm showing some training labels, positives in green and negatives in red. Note that some false positives will slip through because with epipolar geometry, the best that we can do is map points to lines. So it's not a perfect labeling, but it is good enough to be used as an additional supervision signal for training. Then our complete loss formulation goes like this. It's a hybrid loss with two components, a classification component and a regression component. For classification, we just use a standard binary cross entropy with the labels that you just saw. And for regression, we use the weighted 8-point algorithm to compute the essential matrix and then compute the difference between the estimated one and the ground truth essential matrix. The regression loss is quite unstable in practice, so what we do is we minimize first the classification loss alone and then bring the regression loss in to improve performance. Okay, so that's it for the training procedure, but what does our network actually look like? So one distinctive element of our problem is that we have data that is by its nature unordered. So we just have a set of key point coordinates, and ideally we would want the same output for different permutations of the input. This is not something that we can guarantee if we have convolutional or fully connected layers. It is a similar problem to the one faced by PointNet, which is a recent paper on 3D point cloud segmentation. And their solution was to process each point independently with multi-layer perceptrons and then generate a single global feature which is concatenated to each one of the point-wise features. We take inspiration from this, but have a slightly different formulation, which is more appropriate to our problem. So this is our network. As we saw earlier, it takes as input n correspondences, each one with 4 dimensions. It's just x and y coordinates in one image and the same on the other image. And produces one weight for each correspondence, which encodes its likelihood of being an inlier. Then we have 12 residual blocks with weight-sharing perceptrons, which process each point separately. However, if we want this to work, we need global information of some sort, and we show how to do this, how to embed global information into the feature maps with what we call context normalization. So what is context normalization? It's a very simple non-parametric normalization of the feature maps. All we do is we normalize them to 0 mean and standard deviation 1. It's the same operation at training and testing time. There's nothing that is learned. Notice that we applied over the dimension of the correspondences, so what you see in red here, but separately for each image pair in the batch, as it does not make sense to mix the context of different image pairs. And this simple operation helps keep the feature maps well distributed and informative while giving each individual feature a measure of context. So from what we have seen so far, we see that we need only the camera poses to train this. Where do we get them from? We show that we can obtain them without human intervention from large collections of images of the same scene with off-the-shelf structure from motion algorithms. So here I show 2 examples of the types of images that we use, some indoors set on the left and an outdoors one on the right. So let's move on to the experiments. To benchmark our method, we use the following metric. We compute the angular error between the ground truth rotation vector and the estimated rotation vector, and we do the same thing for the translation vectors. Now we can determine whether a pose is accurate or not by simply thresholding over both of them. And what we do then is we compute the mean average precision, or MAP, up to a certain angle. Here I show 3, 5, 10, and 20. Notice that we are doing post-regression, so it doesn't matter if we go much further. If you are off by 40 degrees or 60 degrees, at that point you are just wrong. So we do 2 ablation tests. The first one is to validate the loss function. We have 4 variants. This is the slide that you see. We have only the regression loss in green, only the classification loss in blue, the hybrid loss using both regression and classification in purple, and an additional one which is direct regression to the essential matrix by putting a fully connected layer at the output of our network and just outputting now 9 values, which we take to be the essential matrix. And as you see, the regression loss alone is not enough to train the network successfully. The classification loss does very well, but with the hybrid formulation, we can obtain the best results. We also evaluate the effect of context normalization. So without it, our network, that's the bar in blue, does poorly as expected because there is no global context information. But with it in red, it does very well. Additionally, we consider a point-net style architecture, that's the one in green, using a single global feature, which does quite well, but not as well as our approach for this problem in particular. So that was it for the ablation tests. That was running on a subset of the data, but for the final set of results, we want to train a single model on 2 sequences. One is indoors and the other outdoors. So what we do is we just sample 10,000 image pairs from each and concatenate them to build a training set. That's what I'm showing on the top of the slide. So the outdoor set on the left and the indoor set on the right. We test on the remaining sequences, which are 4 outdoors and 15 indoors. Note that they are completely different scenes from the training data. So these are the numerical results. We benchmark our approach against a number of baselines. Our results are the ones in purple. We have 2 columns because we are using 2 different types of key points to construct the input to the network, shift in a dark color and lift in a bright color. And as the results show, we perform extremely well on outdoor scenes. That's the plot on the top, where we roughly double the state of the art, which is still ransack using lift features. On outdoor scenes, that's the one in the bottom, the changes between the images are not so drastic. So dense methods do actually pretty well, but we still manage to edge them out by a small margin. And more importantly, we showed that we can do much better than ransack, that's the one in orange, with exactly the same input data. One detail that we glossed over is that at test time, we do not require differentiability anymore. So we can actually apply ransack on top of our method. So why would we want to do that? You have to keep in mind that our method is single shot, so it can hardly be expected to be perfect. But it is very, very, very good at filtering out clear outliers. So if we use ransack on the surviving inliers, it can be run much faster because it's running on a small subset of the data. So in total, the computational cost is very small. It's about 17 times faster than standalone ransack on the same data while performing better. So these are some qualitative results. Ransack is on top, and our approach is at the bottom. We show only the inliers, in green if they are under the error threshold, and in red otherwise. So to summarize, we have presented a novel architecture for outlier rejection. We find that training it with a hybrid classification and regression loss is critical for performance and show how to do it in a differential way. And we use context normalization as a very simple and effective technique to embed context in a permutation invariant way. Code and models are up, so if you want to try it, they are on GitHub, and please come visit us in the poster if you would like to know more. Thank you.
So we have time for a couple of questions. So anyone with questions, please come to the microphone in the corridor. So I have one question. Yes. So it seems like your context normalization seems to be very similar to batch normalization. So have you ever tried to learn this scale and shift parameters like in batch normalization?
Yeah. Our network actually has context normalization and batch normalization, but we use batch normalization only to speed up the training. So it actually helps, but what it's doing, it would be mixing all of the samples in the batch, so it's actually counterproductive if you use it only to do what we are trying to do with context normalization.
So if there's no more questions, let's thank the speaker again.
The
The next talk is going to be OATM, Occlusion-aware template matching by consensus set maximization. The talk will be given by Simon Korman.
So the method I will present today, OATM, was designed to efficiently match a template that can undergo both deformation and partial occlusion, as can be seen in the two examples below. Towards this goal, we make two main contributions. The first is a new technique for accelerating template matching in high-dimensional spaces. This is done by a reduction to a product space, which gives a quadratic improvement in runtime. Second is in the ability to explicitly handle occlusion. Here we take a ransack-type approach with measurable guarantees, where the goal is to maximize the number of pixels that agree on intensity up to a given threshold. I should note that our motivation here comes from applications in assured autonomy, such as satellite pose estimation, where time is not that an issue, but every error is costly, and therefore guarantees are highly desirable. Some background. So the classical template matching works in a 2D translation sliding window manner with L1 or L2 similarity measures. This was later extended to higher dimensional spaces, such as in the fast match method, where 2D affine space is used. Here are some more recent methods that handle both occlusion and deformation. On the left, a very nice line of work where the standard similarity measures are replaced with more advanced ones. Specifically, these here are the BBS and DDIS methods. On the right, a large body of work, very active, where neural nets are trained to produce embeddings for image patches, and these embeddings are used in many different applications. Okay, so let me begin by describing how we can accelerate template matching. So here is a template and the many different locations that it can take in the target image. We're looking for the best location, in our case, the one that maximizes pixel consensus. If we denote by D the number of pixels in the template, and by N the size of the transformation space, and look at this search problem in a vectorized mode, we are in this 1 versus N situation in a D-dimensional space. And this can be solved with linear scan in time order of D times N. But we propose instead a reduction to a product space of a set of 2 vectors, each of size square root N. And this is a reduction in the sense that if we manage to find the best matching pair of vectors in the product space, it's easy to infer the optimal solution in the source. Now, it might seem like we haven't done much because matching between 2 sets of square root N vectors might still take time that is order of D times N, but it turns out that this can be done much more efficiently with the help of the random grids hashing algorithm. So we managed to quadratically improve the dependence on the transformation space size N, and this is very significant. We can now handle higher dimensional spaces still in a reasonable time. So what does this look in template matching? I'll show here the product space for 2D homographies, and this generalizes the constructions for the simpler 2D translation and 2D affine spaces. So this is the idea. On the template side, we take a very fine and local sampling, which is an epsilon ball of samples around the identity transformation. So the identity sample is just the template itself, and the epsilon ball is given by all samples defined by quads whose corners are at a distance of up to epsilon from the corners of the template itself. On the image side, we take a coarse and global sampling, an epsilon net of samples that covers the entire space up to a resolution of epsilon. So here we take a 2D grid of resolution epsilon, and we take the samples given by the quads whose corners reside on this two-dimensional grid. This gives us the two sets of samples, U and V, and one thing that we have to make sure is that they are balanced in terms of the size. So we want them both to have a size of approximately square root n, and this is done by tuning the resolution parameter epsilon. Now I can describe the full algorithm. So our goal is to maximize the consensus to optimize this simple functional. The first step would be the reduction that I just showed to build the vector sets U and V. And then we repeat k times in a ransack fashion the following. In each iteration, we sample d prime a small number of random dimensions. In this example, the sample is not good because the last coordinate is an outlier. But still, we reduce the vector sets U and V just to these d prime dimensions, and we get smaller sets U prime and V prime on which we run the random grids method. The random grids tries to find a pair of small vectors that agree on all coordinates. In this case, it will fail, but taking one or several more iterations, in the end, we will get a good sample, and here random grids will find a matching pair of vectors with high probability. Now it only remains to go back to the full dimensional space and actually measure the size of the consensus so that after k iterations, we can return the best transformation found. Moving on to experiments, here I'll just briefly describe some of them. So first, regarding the success guarantees of our method, they're specified in the paper, and we also show them to match the theory. Also, we give a set of standard template matching experiments, which don't include occlusions. Here we compare to the fast match algorithm and basically show that we are just as accurate, on average an order of magnitude faster, and we scale much better. But I'd like to focus first on this robustness to occlusion experiment. Here you can see two examples out of a large-scale experiment. In each, on the top left corner, you can see the affinely extracted template from the image, where we add, on the left side, blockwise random occlusion. On the right instance, we added connected occlusion. Our method does not assume anything about the structure of the occlusion, so it can handle both cases. And our result here is in red, can be seen to match the ground truth. The other methods we compared to, fast match, BBS, DDIS, are not as consistent in handling these occlusions. Here are plots that summarize this experiment. On the top, the errors, on the bottom, the runtime. Both are given as a function of the inlier rate. At the top, you can see our result in orange. We're the most robust to occlusion, and we can handle up to around 70% of occlusion here. In terms of runtime, it's interesting to see that our runtime is inverse proportional to the inlier rate, and this is since we use the standard ransack trick of changing the number of iterations adaptively according to the detected inlier rate. The last experiment is using the recent H-patches dataset. Here, a patch needs to be matched across a sequence of images. And the main challenge for patch matching methods here is to deal with localization errors that are a result of any feature detector that one might use. And these, in this data set, come in 3 different levels, easy, hard, and tough. And in practice, what they mean are they translate into deformation and partial overlap between the pair of matching patches. So you can see here some 2 instances from this data. And we focus on the image matching benchmark here. So what you see here is the entire collection of patches from a pair of images in this data. The standard thing to do here would be to, for each patch, extract a descriptor, and then for every reference patch, search through the target descriptors using nearest neighbor search for the nearest patches. We instead do something much more naive and not as efficient, but I think still that it makes a point. So for each reference patch, we create a template matching instance by taking the complete collection of target image patches and putting them together as one huge collage image. These are the results we get. The numbers are mean, average, precision, and ours is at the bottom. We get very good results compared to some of the state-of-the-art handcrafted and deep learned descriptors. It's harder to see, but we also do better and better as the category gets more difficult relative to other methods. And furthermore, we also think that our results could be improved since we use basically a very naive pixel-to-pixel similarity measure and also a very simple illumination model. Here are some visual results from this experiment, 4 different ones. In each, you can see on the left the pair of patches that are supposed to be matched, and you can see how difficult matching them is in some of the cases. On the right, you can see how our method detects the top patch within the huge collage of patches. Okay, to summarize, we presented a principled template matching algorithm. It's efficient, especially for large transformation spaces. It's robust to occlusions, and maybe most importantly, it comes with probabilistic guarantees. We will make the code available soon, so you can try it out yourselves. Some limitations, so I've mentioned the naive photometric similarity measure that we currently use. We hope to expand on that. And also we think that some of our techniques and ideas can be used in larger setups and not only in template matching, perhaps in the image-to-image matching scenario. Okay, thank you very much. That's it. And please come and visit us at the poster session.
We have time for questions. There are 2 mics on 2 sides of the room for anyone who has questions. Okay, I have a question. Do you see any of these ideas, especially the product space reduction? Do you think it can be used to, for example, speed up convolutional layers in convolutional networks or something like that?
So we only have very initial ideas in this direction. We're working on it now, but nothing yet very concrete.
Good to know. Thanks. Let's thank the speaker again.
Third talk of this session is titled Deep Learning of Graph Matching, so which won honorable mention prize, as you know. The talk will be given by Andrei Zanfir.
Good afternoon, everyone. My name is Andrei Zanfir, and I will present our research on deep learning for graph matching. This is joint work with Cristian Sminchisescu. Graph matching is the problem of computing an assignment between nodes in 2 graphs under structural constraints. We illustrate how graph matching operates by using as an example 2 images of different birds. Our goal is to establish correspondences between the 2 structures. The points in the first image form a graph G1 with a vertex set V1 and an edge set E1. The points in the second image form a graph G2 with a vertex V2 and edges E2. The problem is to find for each vertex in V1 its corresponding vertex in V2. In graph matching, we do not only account for relations between the nodes in the 2 graphs, but also for their pairwise or edge relationships, and the corresponding cost is a global one. The intuition is that there may be structure or semantic correlation between, let's say, the texture or geometry of the bird's beak and its tail that should be preserved among the two images. We expect this relationship to hold across multiple geometric transformations or semantic instances. Dealing with structure introduces additional modeling and computational difficulties. The challenge is to represent meaningful structural correlation, which, however, may be application dependent and difficult to encode by hand. Ideally, they should be learned. For computing correspondence, there are two setups. Geometric matching operates with the same object instance that appears in images from different viewpoints or from a video. In contrast, the main testbed of graph matching is calculating semantic correspondences between images of objects with different appearances but in the same semantic category, usually in different poses and orientations with respect to the camera and possibly at different scales. Existing methods for graph matching typically relax the combinatorial assignment problem, and the initial ones use pairwise node and edge features based on, for example, sieve descriptors or geometric distances or angles. The models have been so far learned only to a limited extent. When learning was performed, it was restricted to the relative weighting of pre-selected feature rather than their parameters. Recently, there has been a shift from hand-designed features to deep hierarchies. Such pre-trained descriptors have been shown to match or outperform hand-designed ones even within nearest neighbor schemes. Today's state-of-the-art formulations refine the deep point descriptors by training a matching cost function. While many of these methods share the same objective of us, training a deep network model for matching, they do not use pairwise node and edge relationship within a global graph matching objective as pursued in this work. We will now review the key elements of our formulation. We encode structure in the similarities between pairs of vertices and pairs of edges in the two graphs to match. We build a special square affinity matrix M having dimension equal to the product of number of nodes in the two graphs. The matrix is indexed in pairs of possible correspondences as follows. Affinities on the main diagonal of the matrix measure the similarity between the nodes in the two graphs. Off-diagonal affinities measure similarity between edges in the first graph and edges in the second graph. Given the built affinity matrix, matching is usually formulated as a quadratic integer program under the one-to-one mapping constraints encoded in a binary matrix C. The problem is NP-hard, and most methods fall back on approximations. One such class of relaxations is to drop both the binary and the one-to-one mapping constraints and enforce a unit norm. In this case, the solution is the leading eigenvector of matrix M. Intuitively, the continuous values in V star can be seen as confidences of how likely the indices in the solution vector represent a correct match. Notice that each index corresponds to a possible pairwise assignment among nodes in the two graphs. To make the framework trainable, we design a loss that measures the deviation between the predicted correspondences and the ground truth. We can work with arbitrary graphs in each image. The graphs to match can be defined on a regular grid or can have nodes in arbitrary positions. Here we show one graph of each type for generality, but any of the four permutation is possible. Our objective can now be stated. We represent the affinity matrix based on deep feature hierarchies, and we train a complete deep graph matching model so that it predicts correspondences that are as close as possible to ones given in a training set. The challenges are in propagating gradients with respect to deep network parameters through matrix function layers, including the ones that solve for graph matching. The question is how can this be done in principle and how it can be made efficient? We rely on the framework of matrix backpropagation previously introduced by Ionescu et al. These represent a generalization of backprop to matrix functions and global layers such as SVD or eigendecomposition. The framework preserves the convenient nature of computing derivatives in reverse accumulation mode as in standard backprop and offers symbolic derivation for layers like eigendecomposition. This is likely to become important when physical constraints in computer vision are integrated within deep models for efficient weakly supervised learning. Implementations of matrix backprop are available in MathCompNet and TensorFlow. One of the key aspects of the derivation is the factorization of the affinity matrix. Zhou and De La Torre introduced a factorization that is generally applicable to many graph matching models. They noticed that when the affinity is sparse, generally the case is the affinity is sparse, as values are assigned only for selected pairs of nodes or edges. Hence, their affinity factorization relies on two important smaller matrices, MU, which is the matrix that measures similarity between vertices in the two graphs, and ME, the matrix that measures similarity between edges. G and H are matrices that completely describe the connectivity of the two graphs. Working with smaller matrices will prove essential for efficient learning. The question now is how to represent MU and ME in a way that can naturally be integrated within existing deep networks architectures. In our model, each image is processed by a Siamese network producing feature hierarchies, U for vertices and F for edges. We can describe MU and ME as Gramian matrices of edge and vertex descriptors computed by the deep network. To build an edge descriptor, we extract features from endpoints I and J of an edge K and concatenate them. For a vertex descriptor, we extract feature at its corresponding position. The figure here illustrates how the affinity matrix layer is computed using a deep network. Graph structure matrices G and H are needed to correctly extract features and in order to build the affinity matrices ME and MU used to compute the affinity. Once the matrix is complete, we must find its leading eigenvector. The power method iteratively multiplies them to the previous or initial solution until convergence. The complexity of this matrix vector multiplication is quartic in the vertex size if M is dense, but fortunately it is almost quadratic when M is sparse, which is also our case. To turn the power iteration into a true deep network layer, we must be able to backpropagate gradients with respect to feature parameters through this layer. We use matrix backprop, which supports matrix functions which are intrinsic in the factorization of M. We compute derivatives expressing the variation of the loss with respect to the variation of Vk plus 1, which is the approximation of the leading eigenvector at iteration k plus 1. A key definition is the one of the inner product of two matrices, which is expressed as the dot product between the vectorized matrices. This is slightly technical, but we can rely on an iterative matrix backprop scheme to compute the gradient of the loss with respect to the matrix M, but we don't do that, because we earlier made a choice of using an explicit factorization for the matrices ME and MU, and this is the reason why. From quartic complexities, without factorization, we go down to complexities that are cubic and quadratic in the number of edges respectively. For relatively sparse graphs, the reduction is significant. We completed the layer requirements, and now we can plug it into our framework to produce the solution V star and backpropagate its gradients with respect to deep features. A bistochastic operation is also transformed into a layer. This is an important step in having the solution obey the one-to-one mapping constraints. The layer outputs a final matrix of assignment S and the corresponding positions of the matches. The final network pipeline is completed with the loss. Gradients are passed all the way from the loss layer to the parameters of the deep networks, producing the pairwise node and edge and features. To test our network, we first learned on Scintilla, a challenging video dataset with dense geometric correspondences. Our tests show that even for large graphs with about 1,000 nodes each, our method takes 2 seconds to complete a forward plus backward pass during training. If the matrix M were not factorized, we would have to work with matrices of size 1 million by 1 million, which is clearly prohibitive. We show improvement over the state of the art as measured by the percentage of correct key points metric. Visually, our estimated correspondences remain on the same surface as the source points, even in the case of large displacement. See, for instance, the wing of the flying monster at the bottom left corner of the image. We also test on several sparse semantic matching problems which are best suited to illustrate graph matching models. The first dataset is CUB, which contains about 12,000 images of 200 word categories with 15 annotated parts. In the plot, we show competitive performance with respect to the state of the art for different operating thresholds. In the qualitative visual matching examples, notice that most correspondences are correct, even when the birds have very different visual appearance. We also test on Pascal VOC, which has key point annotation for 20 semantic classes and obtain competitive performance. Points having the same color in the two images represent different semantic correspondences as estimated by our model. Notice that our model is able to estimate correspondences correctly for objects of the same semantic category but with quite different shape and appearance. Their poses can also vary significantly across the images to match. Here are some more results from Pascal VOC for objects of the same semantic category but with very different appearance. To conclude, we have presented a deep learning formulation for graph matching that is end-to-end trainable. The challenges are the propagation of gradients with respect to the parameters of the deep feature extraction hierarchy through the relaxation solving graph matching. This is difficult due to the presence of matrix function layers and the associated calculations, which, however, can be performed efficiently with matrix backprop. We showed that our model achieves promising results for both geometric and for semantic matching problems. The methodology is potentially applicable to other problems where deep feature hierarchies and graph models are adequate, as for instance in the case of text corpora or for social network models. Before I conclude, I would like to invite you to come by two other posters that we're also presenting today. One focuses on the 3D human pose and shape reconstruction of multiple people from just a single image, using multiple scene considered like a ground plane. The other is devoted to human appearance transfer based on geometric and learning methods, or shortly put, how to get dressed like a celebrity by only using 2 photographs. Thank you for your time.
So we have time for questions. So there are microphones in the front here. So I have one question. So in your work, basically you are taking very typical algorithmic architecture, consisting of this affinity computation and power iteration and normalization, right?
Exactly.
So have you ever tried other sort of algorithmic architectures?
Other graph matching solving?
Yeah, sure.
No, we haven't tried. We found this matrix vector multiplication to be the most easily pluggable into our model.
But maybe extendable, right?
It can be extendable, exactly.
Nice. So any questions? Okay, if not, then let's thank the speaker again.
The next talk is Unsupervised Discovery of Object Landmarks as Structural Representations. The talk will be given by Yuting Zhang.
Hello, everyone. I'm Yuting Zhang from the University of Michigan. It's my great pleasure to present our paper, Unsupervised Discovery of Object Landmarks as Structural Representation. An important goal of computer vision is to enable the machine to understand visual structures, such as object poses, contours, and 3D shapes. These structures are physically conceptualized and perceptible by humans. Deep neural networks have shown remarkable success in learning latent representations with many desirable properties. However, the structures of those representations are not conceptualized or interpretable. To bridge the gap between the latent representation and the explicit structure, supervised learning methods require extra human annotations. They are often costly to obtain and unavailable for most object categories. Then it comes to the question, can we use deep neural networks to learn image representations of explicit structures? To study this problem, we consider a particular type of structure, the object landmarks. We define the landmarks as the salient points that are semantically consistent across objects in the same category. They can encode the shape and pose of an object compactly, and they can be applied to many object categories. To extract the representation of an object, we propose a model to discover the landmarks as a structural component. Our model can also extract additional latent features based on the landmark locations, making the representation more informative about the object appearance. Taking the representation as an intermediate step of a bigger pipeline, we can optimize the landmarks and latent features for a downstream task. Particularly for unsupervised learning, we take the image reconstruction as a generic driving force to learn the representation. This leads to an autoencoder framework. Under this framework, we address the challenging problem of unsupervised object landmark discovery and make our model work for different object categories. The whole framework is realized by a fully differentiable neural network. In the backward path, the image reconstruction can encourage the model to learn informative landmarks and features. Now, we expand our framework to an overview of the neural network architecture. Let's nail down to the model for unsupervised landmark discovery. The key components are the differentiable formulation and the unsupervised constraints to define a valid landmark detector. Our model is inspired by Singhis et al. Study, but their formulation is not differentiable. Similar to a one-shot object detector, our object discovery module uses a convolutional neural network to get a detection heat map. The network has an encoder-decoder architecture with skip links. We normalize all the heat maps, including the background, using the softmax across channels. From each foreground heat map, we get the coordinate of a landmark. More specifically, we approximate the foreground heat map with an isotropic Gaussian. We take the mean of the Gaussian as a landmark coordinate. Essentially, it is an averaged coordinate weighted by the foreground heat map, and this is differentiable. But so far, the output of our model are not guaranteed to be valid landmarks. In other words, they can be arbitrary latent features without explicit physical meanings. We define 3 unsupervised soft constraints to make the landmark detector desirable. A good detection heat map should have its value concentrated in a small local region. We achieve this by encouraging the isotropic Gaussian variance to be small. And in the later training stage, the heat map can become more concentrated. Different landmarks are expected to localize different visual semantics. We penalize the model if the pairwise distances among landmarks are too small. The most important property of a landmark is to localize a visual semantic pattern stably. Suppose we have a transformation that is not destructive to the visual content. When it is applied to the image, the landmark should move accordingly to the same transformation. Only in this way, the landmark can localize the same pattern stably. This property is called the equivariance, and it can be constrained by this equation. Singhis et al. Used the equivariance for landmark discovery by defining a training objective on the detection heat maps. In contrast, we can apply the above equation directly on the landmark coordinates with the help of our differentiable formulation. Following Singhis et al., we use random simplet spline to simulate the image deformation. When videos are available, we can also compute the optical flows and use them as the transformation during training. With the above unsupervised constraints, our model can discover valid landmarks. Now let's move on to the landmark-based extraction of the latent features. Our key idea is to perform a weighted average pooling around the landmarks using differentiable masks. In more detail, we extract a convolutional feature map from the image. Then for every landmark, we take its corresponding Gaussian heat map as the mask for the average pooling. As an illustration, we pixel-wisely multiply the Gaussian heat map of the first landmark with all the channels of the feature map. We reduce the reweighted map to a single feature vector by spatial summation. We do the same thing to the other landmarks, and also similarly for the background. Putting things together, we obtain a stack of local feature vectors for the landmarks. After the feature extraction, the last component of our model is a landmark conditioned image decoder. It reverts the landmark localization and feature extraction. According to the landmark coordinate, we generate a Gaussian heat map with a fixed variance, and we perform normalization across channels. For the local feature of every landmark, we duplicate it at each pixel to get a convolutional feature map. We take the heat maps as the reweighting factor for the feature maps. All the reweighted feature maps are summed up together to form a single tensor. We also concatenate the heat maps to this tensor and feed it to another neural network for image reconstruction. So far, we have reverted the encoding procedure and complete the model definition. Now let's take a look at the key experimental result. For unsupervised landmark discovery, Sminchisescu et al.'s work is the only one that we can compare with. Both methods can discover reasonable landmarks on facial images. However, their method can sometimes make significant mistakes. We highlight the incorrect landmarks with red circles and indicate the correct locations with green dots. These mistakes are mostly due to large pose variation and occlusions. In comparison, our method produces more stable results on the same images. Our method can also discover more landmarks on not well-aligned facial images, like this. We also evaluate our model on cat head image and on more objects, including shoes, digits, cars, and wild animals, and also on the human body. The human dataset has data in video format, so we use optical flow as additional self-supervision for the equivariance. The unsupervised structure discovery of complex objects like human bodies are very challenging, but our model can still get reasonable landmarks. To evaluate our method quantitatively, we train a linear regression model to map the discovered landmark to the human annotated landmark. So an ordinary landmark detector can be obtained without fine-tuning the neural network. On the MAFL face dataset, our model outperformed the Sminchisescu et al.'s method, even when their method used more discovered landmarks or a dense object free. And surprisingly, our method also outperformed the off-the-shelf supervised method. In addition, with only 500 labeled samples, our linear regression model can already achieve very good performance. This is a strong result for semi-supervised learning. For the other types of objects, our method can also achieve better results than previous unsupervised method. For more quantitative results, we evaluate the effectiveness of our discovered landmarks as visual features. In particular, we consider the binary classification of shape-related facial attributes. As shown in the table, the classification accuracy based on the landmark coordinate alone are pretty good. And this is better than using the pre-trained FaceNet features. Finally, I'd like to show that our autoencoder framework can naturally produce a good image generator conditioned on the landmarks. And our discovered landmarks are disentangled from the latent feature automatically. In particular, we keep the latent feature fixed and manipulate the discovered landmarks to generate new images. As the figure shows, the facial shape, expression, and pose make changes according to the landmarks. The other appearance factors are kept the same. And here is another example. And it also works for human body images. To conclude, we address the challenging problem of unsupervised object landmark discovery, and we formulate it as a sub-problem of representation learning with explicit structures. We propose a fully differentiable neural network architecture to tackle this problem. And our unsupervised model can produce meaningful landmarks, show competitive performance to supervised facial landmark detectors, and provide a neural network interface that the human can manipulate. With that, I hope our work can inspire more studies on the unsupervised learning of perceptible and interpretable structures. Thank you very much for your attention.
As we handle questions, would spotlight presenters please start lining up by the stage? We have very limited time to change between spotlights. Any questions? Okay, let me ask a question. Your work, as you mentioned, was inspired a lot from the work by Trulls et al., and you showed pretty significant improvements from their approach. Yeah. What aspect of your model did you find most important for those improvements?
I think actually several aspects. The first thing is we have a fully differentiable formulation. It actually makes the definition of the unsupervised learning objective function much easier, and I also make it much more effective. And we also can get training signals from the downstream task, that is the image reconstruction, which is also useful. And finally, I believe we also use a stronger neural network architecture, and our architecture can capture a little bit higher level information. And this is also helpful for the landmark discovery. Yeah. Thank you.
Let's thank the speaker again. Oh, actually, there's one more question.
Hello? Yeah. So first, I'd like to say this is a really cool paper. I really enjoyed it. This is very neat and kind of a, out of the box. But I was wondering if you have thought of making it a little bit more out of the box even. You're assuming that these the features should be X, Y points, right?
Right.
Is that maybe we should get rid of even that assumption? Maybe they should be lines or curves or I don't know, smiley faces or
Right, yeah.
Is there any reason they have to be XY points?
No, it don't have to be XY point. Actually, I also thought about similar problem to make it line or something, but XY point is the simplest. So this is my first paper about this in this direction. So actually in the future, I think it will be quite interesting to consider other maybe geometry or even some geometry in the high dimensional space. I think that will be an interesting direction. Yeah. Thanks.
There's actually one question on this side before we end this session.
Yeah, so I have another question about, for unsupervised landmark detections, you have three criteria how to suggest a good landmark. One of them is all the landmarks should capture different semantics.
Yes.
So you penalize that with the similar semantics.
Right.
So my first question is, how did you select those three landmarks? And the second is, when you have this type of penalize, does this your work on, say, outdoor structured data set, those kind of images?
Yeah, so your first question is the number of key points or something?
So the number of the three unsupervised constraints that you use for training the landmark.
Okay, your question is how I designed this, right?
Yeah.
Okay, sure. Yeah, so for the landmark, the equivalence is the most important thing. Yeah, so this is something quite apparent, and we must do this. But if we only do this, we can get some trivial solution. The first constraint is the concentration constraint. If without that it's possible, we can get 2 peaks or multiple peaks on the heat map. And in that case, my formulation will not work. So the first constraint is to make the heat map to have a single peak. And for the second is separation loss. The separation loss is necessary because in the beginning, your heat map is random. And for random heat map, all the landmark, remember that they are the mean coordinate. They are all around the center. So they have similar initialization. So in this case, if we just train the neural network, we can have a very bad local minimal. That is, all the landmark will just exactly at the center of the image. And this separation loss can avoid this kind of local minimal. Yeah, and for your second question, can you remind me?
Yeah, so if you have the penalty term for penalizing semantically similar landmarks, how well does your method will work on the building data set, for example, outdoor landmark data sets?
Actually, I haven't tried that. Yeah. So I don't think I can give you a definite answer on the building data set or the kind of thing. Yeah, but basically, the assumption is all the object instance should share some similar architecture. If they are similar building, probably it can work. But if they are quite different building, maybe not. Yeah.
Thank you.
In the interest of time, let's thank the speaker again.
Yeah, thank you.
We'll now have the spotlight presentations.
Hi everyone, this is Bo Chen and Scamantus Klikas. We're here to tell you about integer quantization. Over the past 2 years, computer vision applications have happened in real time on real devices, all thanks to neural networks. Neural networks are actually over-parameterized, most of them, but now researchers have given us architectures like mobile nets that can actually operate on the real-time range, and also have given us techniques like quantization to help us reduce the complexity of most networks. However, most of the compression techniques actually focus on networks that are heavily over-parameterized from the beginning. Therefore, our focus in this paper is actually to compress networks that are efficient by design and that are powering real-time applications. And we do so by quantizing the weights and activations of our networks using 8-bit integers. We provide an efficient inference and training framework and show that it works on mobile architectures.
Quantization helps a lot with mobile devices. 8-bit weights and activations reduce memory pressure for them smaller and fit better into cache. On most mobile devices, there is integer-only SIMD operations that make integer-only inference much faster than floating point inference.
So we quantize a floating point value r into an integer q using an affine transformation. The scaling factor s is a float, and then the offset z is an integer. Z always maps to float 0, therefore it's called a 0 point. We can also quantize an entire vector by sharing the scaling factor and the 0 point across the entire vector. So here, pictorially, we just map every floating point vector to its closest integer grid. And also, that's how we quantize entire vectors. All right, so how do we do inference with this quantization scheme? Well, let's look at a simple example where we just multiply 2 vectors together. The quantized version of this graph basically quantize their inputs and then multiply them using integer multiplication and then dequantize the output. So for dequantization, we need to know the scaling point and the 0 point of the output, which they can be both learned from the data directly. We can also use this quantization scheme to quantize something that's even deeper. Notice here that apart from the final dequantization step, everything here is done with integers, which means that the entire inference can happen on integer-only hardware.
To get accuracy similar to floating point models, we train with quantization. This way, the weights adjust themselves automatically to quantization artifacts, and the loss at the top forces outputs to be similar to floating point model outputs. This is the simple case. With batch norm, things get a lot more complex. If you're interested, please see our poster. Weights and activations get quantized differently. For weights, we know all the values, so we just take minimum, maximum, clamp to that range, and quantize. Activations depend on inputs, therefore we have to collect the values during training, run a slowly moving, exponential moving average on minima, maxima, and then use those to clamp and quantize.
So how are we doing? Using MobileNet architecture, we can actually have a across-the-board improvement in terms of the speed-accuracy trade-off, both in terms of ImageNet classification and COCO detection. Better yet, 8-bit quantization is fully incorporated into TensorFlow, which means that with these few lines of code, you can already start to train and deploy your models on mobile in 8-bit. And finally, if you have any questions, please come see us at our poster E22.
I'm Grant Van Horn, and I'll be discussing our paper on multi-class crowdsourcing. To motivate our problem, imagine you're building a bird classification data set, and you'd like to identify the species in this photo. There are about 10,000 bird species in the world, so this is a large multi-class problem, and some species, even in the same geographical region, can look very similar. So you post the image to a crowdsourcing platform and hope that the crowd can help you identify the species. And imagine that you get the following 3 responses. User A and B believe that the photo is of a snowy egret, and user C believes that the photo is of a great egret. Now what you're after is a model that, given the image and the sequence of annotations, can output a final species prediction. One popular instantiation of this model is to simply do majority vote, and this model would output snowy egret as the final prediction. But previous work has shown the benefits of learning the skills of the workers, represented here as confusion matrices, and taking those skills into account when predicting the final label. And a model that does this would learn that worker C is more skilled than workers A and B, and the final prediction would be great egret. We extend prior work and tackle new problems in this domain that have not been considered before. First, our model can adapt to a large number of classes, such as 10,000 bird species. Second, our model can handle a dependence between the worker responses. And third, our model can jointly train and use a computer vision system. So when there are a large number of classes, the traditional approach of learning a confusion matrix of skills for the workers breaks down. And this is because of statistical and computational complexities that arise when trying to estimate the parameters of such large matrices. For example, even when restricting our problem to birds that occur only in California, we would still be estimating matrices with about 900,000 entries for each worker. Our model takes advantage of a taxonomy across the class labels, and rather than learning one big confusion matrix, our model learns a confusion matrix at each inner node of the taxonomy. This provides 2 benefits. The first being that our model can adapt to worker responses that come from a taxonomy rather than a flat list. And secondly, this approach provides significant parameter savings, making the problem more computationally and statistically tractable. So rather than estimating 900,000 parameters, we're down to about 14,000. In the majority of prior work on crowdsourcing computer vision tasks, it is assumed that worker responses are independent, so the workers just analyze the image and do not see each other's responses. In our work, we tackle the problem where workers are allowed to see all previous responses, and our approach to handle the dependence amongst responses is to not only estimate a worker's skill, but to also estimate each worker's perception of other workers' skills. And so in this example, we're visualizing the notion that we learn both worker C's skill across the classes, and we also learn worker C's perception of the other worker's skills. And when predicting the class label for an image, we combine all this information together, allowing us to model that a worker's response may be biased by the previous responses. And finally, our system is essentially a big hierarchical Bayesian model, which incorporates class priors. Usually these class priors are fixed regardless of the particular image being annotated. But we jointly train a computer vision system, affording us multiple benefits. First, the computer vision output is used as the per image class priors. And secondly, if the computer vision system is confident in its predictions, then we may not require any additional human responses. And so our work comprises these contributions. And when put together, we can achieve significant improvements over majority vote. In this example, we achieve a 90% decrease in label error. This system is currently being deployed on the citizen scientist website, iNaturalist, and please visit our poster if you'd like to see more results and learn about the implementation. Thanks.
Hello, I'm Yu Cao from Tsinghua University, and I will have a brief introduction of this paper, Partial Transfer Learning with Selective Adversarial Networks. Transfer learning solves the problem when insufficient label data are available in the target domain with joint distribution Q. It typically leverages the off-the-shelf label data from a different but related domain with joint distribution P. P is not equal to Q. But as shown in the figure, existing transfer learning methods assume that the source and the target share the same label space, and this is always not satisfied in the real-world applications. In our work, we introduce partial transfer learning. It relaxes the assumption to that the target label space is only a subspace of the source label space. There exist 2 main challenges. First, we need to enable positive transfer between the shared part of the source and the target label space. Second, we need to circumvent
negative transfer between the outlier source label space and the target label space. We enable transfer learning by adversarial learning. Adversarial learning can force the backbone network to learn features invariant for the source and target domain to confuse the binary classification network, discriminating the source and the target domain. This is a structure of our method. It composes of a backbone CNN network and number of classes adversarial networks. Each adversarial network GDK is responsible for classifying the source and target data of class K. We define two weighting mechanisms. One is the instance weighting for each data instance. Height Y is a predicted probability distribution across source label space. Each dimension of height Yi represents how much the data instance Xi belongs to the corresponding class. Thus, as shown in the right part of the formula, we can use each dimension of the height Yi to weigh the deep feature of Xi to the corresponding adversarial network. Another is class weighting to downweigh the influence of the adversarial networks for the outlier label space. Since target label space is excluded with a source outlier label space, the probability of the target data predicted to belong to the outlier label space is very small. We sum the predicted probability distribution that height Y of the target data and normalize them as a class weight for each source class. The class outlier label space will have very low weight since every target data has low probability in this class. Here is the overall loss of our work. It composes a classification loss consisting of a cross-entropy loss and an entropy minimization loss on the first time, and the multiple adversarial loss with two weighting mechanisms. This is a setup of our work. We perform experiments on 3 datasets. These are the results of our work. SAN outperforms all the comparison methods, especially on large dataset, ImageNet, Caltech. Our method is robust to the number of target classes and converges fast and well. SAN has a TSNE visualization of nice classification and domain structure. In summary, we introduce a novel selected adversarial network for partial transfer learning in this work. We simultaneously circumvent negative transfer by selecting outlier source classes and promote positive transfer by matching shared class space distributions. The code will be available soon in our GitHub group, and the archive version of our work has already been cited by another work in CVPR. Thank you.
Good afternoon. My name is Simon Yenni, and I will present this joint work with Paolo Favaro on self-supervised feature learning by learning to spot artifacts. The main goal of our work is to learn good image representations from images without any manual annotation. These representations can then be transferred to other tasks, such as classification or detection on smaller data sets with labels. Our approach is to define a new learning task. Rather than using manual annotation, the labels are generated from the data itself and therefore come for free. This approach is called self-supervised learning. The main challenge in designing a good self-supervised learning task is to make sure that it is closely related to semantics and that it cannot be solved by exploiting shortcuts. Our proposed task is a classification of images into real images and images with artifacts. Solving this task will require the model to spot artifacts such as missing object parts or inconsistent textures. Understanding the semantics of an image is often required or at least helpful when solving the task. We therefore train a classifier C on real and corrupted images to learn features without any human annotation on large unlabeled datasets. To generate the artifacts in images, we use an autoencoder and manipulate its learned hidden representations. In order to generate non-trivial artifacts, we use a damage and repair strategy. First, we randomly corrupt feature vectors in the hidden representation of an autoencoder, and then we repair the corrupted representations only locally. This process will result in global inconsistencies. Locally, however, image patches and textures will look realistic. To avoid shortcuts by detecting the decoder fingerprint, autoencoded images are fed as real images to the classifier. The resulting network feeds an image through two pre-trained autoencoders E and D with shared weights. The two autoencoders generate real images at the top and images with artifacts at the bottom. Features are corrupted according to a random binary mask and then repaired by a repair network R. The repair network is interleaved with the decoder layers and has a small receptive field. We only allow the repair network to modify the corrupted features. The classifier C and the repair network R are trained in an adversarial manner. The classifier also predicts the corruption mask. This provides an additional supervision signal. We then evaluate the features of an AlexNet-based classifier on standard transfer learning benchmarks for unsupervised feature learning methods. Our fine-tuned features achieve state-of-the-art performance for classification and segmentation on Pascal VOC. We also evaluate our features by training linear classifiers on top of frozen convolutional layers and achieve new state-of-the-art on ImageNet for all layers. Thank you very much for your attention, and please visit our poster, number F9, for more results and details.
All right, I'm Wei from Duke University. So today I will briefly introduce our work, Low-Dimensional Manifold Regularized Neural Network. This is a plug-and-play network regularization technique that focuses on the geometry of both the input data and the output features. Deep neural networks have proved very successful on archetypal tasks for which large training sets are available. But when the training data is scarce, they typically suffer from overfitting. Many widely used network regularization are data independent, and the efficacy is often limited. The data-dependent regularizations are mostly motivated by the observation that data typically samples from manifolds. But the underlying manifold is usually hard to parameterize explicitly, and sometimes you need the human input of tangent vectors. Okay, we proposed a low-dimensional manifold regularized neural network. It focuses on the geometry of both the input data and the output features. And we don't need to explicitly parameterize the underlying manifold. The idea is, given a bunch of input data xi sample a collection of data manifold n in the Euclidean space RD1, we would expect that a good feature extractor f theta should be a smooth function over the data manifold. Therefore, the concatenation of the data and the feature should still be a low-dimensional manifold, this time in the Euclidean space RD. We call this manifold data feature concatenation manifold. So we suggest that network overfitting occurs when the dimension of m is too large after training. To reduce overfitting, we explicitly penalize the original loss function with the dimension of ml. So basically here, j theta is the cross-entropy loss function, and the second extra term will be it's basically a weighted sum of local dimensions. And this problem is solved using alternating minimization with respect to m and theta. And the key step is to solve a Laplace-Beltrami equation over a point cloud without discretizing the differential operators. So here is the result of LDMNet on the MNIST dataset. We compare the different regularizations sharing the same baseline architecture. As you can see, the advantage of LDMNet is significant when the training data is scarce. Visually, you can also verify that the features learned by LDMNet typically sample lower dimensional manifold as compared to other regularizers. You can say pretty much the same thing for SVHN as CVPR10. Another application of LDMNet is the heterogeneous face recognition. So in this experiment, we want to match a probe image of the subject captured in the near-infrared domain to the visible light domain. If you use DNN pre-trained on visible light images, they typically map images of different modalities of the same subject to the same to separate clusters. Our idea is to use LDMNet to embed features nonlinearly of the different modalities to the same low-dimensional manifold. Awkward silence. Okay, so here is the result. As you can see, the VGG face, which is DNN pre-trained only on visible light images, if it only has accuracy of 74% on the heterogeneous face recognition task. However, after embedding the features using LDMNet, the accuracy can be easily pushed to 85%. Visually, you can also verify that LDMNet will map features of different modalities to the same low-dimensional manifold, whereas other regularizations still map images of different modalities to separate clusters. All right, thank you.
Hello, everyone. My name is Laurens Lamaten from Facebook AI Research, and today I'll be presenting joint work with Gao Wang, Xicheng Liu, and Kilian Weinberger from Cornell University. And our paper is entitled Condensed Nets, an efficient dense net using learned group convolutions. If one wants to deploy convolutional networks in mobile phone applications, computation quickly becomes a major bottleneck. In convolutional networks, by far the computationally most intensive operation is the convolution. To reduce these computational costs, several recent convolutional networks replace standard convolutions, as depicted on the left, by group convolutions, as depicted on the right. Group convolutions split the input and output feature maps into G groups. Output feature maps are only connected to input feature maps from the corresponding group. This reduces the computational cost by a constant factor of G, where G is the number of groups. In this paper, we develop a more flexible group convolution in which the groups are not predefined. Instead, we learn the group structure of each layer during the training of the network. We show that such learned group convolutions can be more accurate and efficient than standard group convolutions and can lead to state-of-the-art convolutional networks for use in mobile applications. The basic idea of our approach is to start from a standard convolutional layer and during learning, progressively sparsify this layer by pruning connections within the layer, as illustrated in the center of this figure. The pruning is constrained in such a way that output feature maps from a single group, for instance from the red group, are all connected to the same feature maps in the input layer. This allows us to convert the sparsely connected layer into a standard group convolution after training is completed, with the help of an index layer that selects and reorders the input feature maps. This process is illustrated on the right. Because we can implement our final model using standard group convolutions, which are well supported by various deep learning frameworks, our implementation is very efficient at test time. During training, we employ a scheme that progressively prunes away connections from the network in 3 stages, and we use a cosine-shaped learning rate schedule. To encourage groups of filters that are relatively unimportant for the final classification decisions to have small norms, we use a group lasso regularizer that encourages the desired sparsity pattern during learning. We incorporate the learned group convolutions into a densely connected convolutional network. In contrast to the original dense net, we use connections across pooling layers, as illustrated in the figure. We also double the growth rate of the network after each pooling operation. We found this further increases the efficiency of our models. We compared our condensed nets with 3 other efficient convolutional networks on ImageNet. Compared to MobileNet v1, our condensed net achieves the same accuracy with 40% fewer parameters, half the number of flops, and much better practical performance because we don't rely on depth-wise convolutions to get lower flops numbers. Depth-wise convolutions perform very poorly in practice because they make the computation completely memory-bound. Compared to the recently proposed MobileNet v2, the accuracy of a condensed net with the same number of flops is still quite comparable. Our condensed net still requires fewer parameters than MobileNet v2, and again, it does not resort to the use of depth-wise convolutions that give poor performance in practice. We have released code and pre-trained models on GitHub, and if you want to see more or learn more, come see us at the poster. Thank you.
Hello, everyone. My name is Zitao Chen. I am with Vision for Robotics Lab from ETH Zurich. This talk is about introducing our work on learning triplet discrete with scale-aware triplet network. So in triplet network, 3 patches are propagated through 3 copies of the same network, generated 3 discretes on a positive distance dp and a negative distance dn. Different triplet losses has been proposed to make dp to be smaller and dn to be larger. The goal is to obtain similar discrete for similar patches and dissimilar otherwise. Such losses are antisymmetric, which means that the loss act equally strongly on both dn and dp, but push them in opposite directions. We can therefore define a conceptual threshold in the middle of dn and dp for this triplet. Compared to CMS network, which has a fixed conceptual threshold to separate all pairs, triplet network has different thresholds. And this help it to learn faster than pairwise network. However, this also introduces a problem. If we increase both dn and dp at the same time, the loss of the network does not change, but the consistency of the discrete scale deteriorates, a problem which we define as local limited context problem. To solve this, we train both CMS and triplet network to learn a 2-dimensional discrete on the minis dataset. The right figure shows that, so if you look at the digit 1, it is actually badly scaled. So large positive distance in digit 1 are compensated by just pushing that cluster away from the others. In this work, we propose our mixed context loss, which means the triplet threshold with a global threshold. The motivation is to bring together the best of both advantages, the fast learning of triplet network and the consistent scaling of CMS losses. So the middle figure shows the discrete generated by our mixed context loss. It is clear that the discrete are consistently scaled and also achieve the best performance, which back out that it can profit from the advantage of both CMS and pairwise network. We also build our mixed context loss on the L2 net and compare with several other state-of-the-art algorithms on the UBC dataset. And FPR95 score was reported on each testing scenes. So the table shows that our mixed context loss achieved the best performance on 4 out of 6 testing scenes. On the other 2 cases, we also achieved similar performances as the best one, which is based on a pure triplet loss on T3net. We also report results on the H-patch benchmark. So we compare our algorithm with L2net and HARNet. Different type of noises were added to the dataset to test the robustness of the network. We report the mean average prediction, and the larger is better. So you can see that our network still achieved the best in all 3 testing cases. So you can check the detail of our paper in F18 poster. In conclusion, we just propose a new loss in this paper that combines the advantage of both CMS and triplet network. Thank you.
So hi, I'm Zhang. I'm going to present our paper, Decoupled Networks. Convolution has been a successful standard module in computer vision. Compared to MLP, it incorporates some key priors into the architecture. Specifically, we can view convolution as an inner product-based convolution, similarity in a sliding window fashion. However, we raise the following questions. what inner product is the best similarity measure? And is it possible to design better similarity prior for some specific tasks? To explore possible solutions, we investigate the behavior of convolution in feature space. We observe that the original feature space inner product-based convolution learns naturally to couple features. The features shows that how those features of each category in eminence look like. Each fan in the figure corresponds to one set of feature in each category. Obviously, the norm of features corresponds to intra-class variation, while the angle corresponds to the semantic difference. Inspired by the decoupling nature of convolution, we explicitly model the intra-class variation and the semantic difference within the decoupled convolution framework. More specifically, we rewrite the inner product-based convolution into the decoupled form. A natural extension results in the decoupled convolution, which is a product of two functions. The first term models the intra-class variation, while the second term models the semantic difference. Here's one example of how we may design the functions. In hyperspherical convolution, we project both weight and input onto a unit sphere, which simply discard all magnitude information. The effect can be easily seen in the 2D eminence visualization, where the feature vectors tend to concentrate into small circles. One way to justify this operator is to observe that the information of images is contained in the phase of Fourier transform rather than its magnitude. Building upon SphereConf, we propose several variants of magnitude functions. For example, we may project the input onto unit ball instead of a unit sphere, and we may have maybe soft version of those operators. And we'll also try some different angular functions as shown below. In addition, we noted some advantages of bounded magnitude functions. First, it can improve optimization, adversarial robustness because it constrains the Lepetit constant in each layer. And second, it can improve optimization, which is theoretically and empirically shown by some recent papers. As an example, we found that such properties can improve optimizations in GAN. We conducted experiments with the CNNs on CIFAR 100. Our results showed that the proposed decoupled operators can improve significantly over the baseline when BN or ReLU is not applied. We have also shown that the decoupled operators work well on ImageNet dataset. Especially, we show that for specific architectures, decoupled operators have advantages over the baseline. We have shown the learned filters of the first layer in below. Finally, we show that the decoupled operators with bounded magnitude are naturally robust against adversarial attacks, either with natural or adversarial training. The figure shows that it would generally require larger adversarial perturbation measured by L genome to attack our model. And thank you. Please drop by for our posters. Thank you.
Hello, I'm Yuki from Kwang University. I will introduce our work on deep adversarial metric learning. Metric learning aims to learn a new distance metric that maximizes the inter-class distances and minimizes the intra-class distances. For most objective functions in deep metric learning, those hard training examples, especially for the hard negatives, plays a very important role in the training procedure as they produce large gradients, while those easy negatives produce small gradients and they contribute little. Many recent works have studied that sampling matters in deep metric learning. They aim to mine hard negatives for effective training and just throw away those easy negatives. However, as there are much more easy negatives than hard negatives in the training set, a natural question is raised. Are easy negatives really useless? In this paper, we discussed that some easy negatives may have potentials to become hard negatives. For example, we can easily distinguish these two faces from their colors of the skin as easy inactive, but they do have some similarities in their facial landmarks. So rather than just ignoring them as most hard inactive mining methods do, we aim to exploit them through adversarial hard inactive generation. With small changes, easy inactives may become very meaningful hard inactives. Instead of directly using the original negative samples for training, we generate synthetic hard inactives at first through the generator. The losses contains two parts. Jm is the supervision signal for the distance metric, where we can employ the existing losses. We use the contrastive loss, trivial loss, lifted loss, and unpaired loss in our experiment. JREG, JHard, and JAdversarial are for the generator. JREG limits that the generated negatives should not be too far away from the original negatives. JHard encourages the hard generated negatives in the original feature space. And JAdversarial is for the adversarial relationship between the generator and our learned metric. We train the network in an end-to-end manner, and this is the overall objective function and the detailed hard negative generator term. We conducted experiments on 3 benchmark datasets. We observed that we can successfully boost the performance of conventional contrastive loss and triplet loss, as well as the more recent lifted loss and unpaired loss on all the 3 datasets. In conclusion, hard negative mining ignores large numbers of easy negatives, but we tap their potentials through adversarial hard negative generation, and they provide essential complements for training. Thanks for your attention, and please stand by our poster for more details.
This is the end of our session. I'd like to thank all the speakers again.